I'm going to start with the table that I asked you to memorize about 6 days ago. So I like to call this chart Home Depot. You'll understand why. You do not need to memorize all of this in the middle. So here's how you use this chart. Do not worry about memorizing all of those words. You do not need to do them. In fact, if you just think of this as a big equal sign, the middle column can be replaced with a big equal sign. You put a number 1 here, and you can put a big number 1 over here if you like. What this means is one of any one of these is equal to whatever the numerical symbol is over there. So por ejemplo, 1 mega equals 10 to the 6. 1 micro equals 10 to the minus 6. 1 pico is 10 to the minus 12. Does anybody have a question? Don't worry about the words in the middle. You do need to worry about the prefix and the symbol. Be careful that the case of the symbol makes a difference. Capital M is mega, lowercase m is milli, strict m is micro. In other words, m capitalized is 10 to the 6, lowercase m is 10 to the minus 6, nope, it's 10 to the minus 3, and then a scripted m, that's a Greek m actually, micro, is 10 to the minus 6. So case matters. Memorize the prefix, the letter, and the numerical values. Many of you already know probably most of these, especially if you learned that King Henry died drinking chocolate milk. I don't use that system. It has its uses, but it's very limited. In the sciences, we go far beyond just the metric range that King Henry covers. We also do area and volume, which King Henry would absolutely give you the wrong answer. If you try to do area or volume conversions with King Henry, you'll absolutely get it wrong. So just be aware. It's a wonderful starting point, but I'm teaching you the correct way to do it now for chemistry, physics, medicine. You can put, because these are called prefixes, or prefaces, if you want to use the correct plural form of prefix. A prefix means it comes in front of something. So what does it come in front of? It comes in front of units of measurement. So for example, we could put a millisecond. 1 millisecond. Whatever unit you put here, you have to put here. 1 millisecond equals 10 to the minus 3 seconds. That's how that chart works. I'm going to erase that because I'm going to use another unit. 1 centigram equals 10 to the minus 2 grams. 1 nanoliter equals 10 to the minus 9 liters. Memorize the prefix, the symbol, and the number factor, and you'll own many useful tidbits to solve the kinds of problems that you're going to encounter for the rest of the year. So the topic that we're on is called unit conversion. It's the process of changing a measurement from one language to another. Now please take a look at my meter stick. This is 1 meter. If I rotate it this way, it's now 3.3 feet. 1 meter, 3.3 feet. 1 meter, 3.3 feet. The size of this stick did not change, but it sounds like it did. You said 1, now you said 3.3. No, the size of the stick remains the same. The language with which I express its size changes. If I'm waving at you and I say hello, and now I say hola, I didn't change anything but the language with which I'm expressing my sentiment. Greetings. And that is what dimensional analysis or unit conversion does. It takes something, a fact that will not change, a size, a dimension, and it changes the language, but not the size of the object. It changes the language with which it's expressed. Okay, that's the first thing to say. The second thing I wish to communicate to you is that I'm going to use a 4-step problem-solving method. It's been in your notes for the same amount of time, I believe, as the prefix table. I believe I first put it in there October 8th. If you read the notes, you saw my little drawings of the guy on one side of a cliff trying to deliver flowers to the girl on the other side of the cliff, separated by a shark. That's my analogy. That's my picture of what we're going to do. Life is a series of problems, or challenges, if you want to say it more optimistically. Life is a series of challenges. If it weren't, it would be quite boring. Life is a series of challenges or problems. One day you'll have a career based on solving problems. Almost every career you can imagine is simply a function of solving somebody else's problem. Ooh, I need to sell something. Can you help me sell it? I need a commercial. I need a print magazine ad. I need a radio spot. I need an internet ad. And you solve their problem. They need something sold. You look at what they're selling. You look at the market. You try to figure out a way to communicate what they're selling as a need. You create a desire for what they're selling. That's your job if you're in marketing and sales, commercial, advertising. The same technique that I'm going to show you that you can use to solve dimensional analysis can also be applied to other numerical problems, but it can also be applied to word problems, logic problems, and even beyond logic problems. The four-step problem-solving method can be generalized to solving even life problems, because there's really no difference between life problems and chemistry problems. You're given information, you're requested a particular result, and it's up to you to build a bridge between the given information and the desired outcome. So these are the four steps. How far you wish to apply them, that's your business. But it's a good problem-solving technique. Step one is to always, and you can write this in your notes if you're taking notes, and you should be. Step one is to know where you are, know where the starting point is. What is the starting point? Step one, what is the starting point? And if you read my notes, I illustrated the starting point with some guy standing on a cliff with a flower, and that's us. That's where we are. We're at some place, and before us is a cliff, a drop-off, a chasm, a deadly, dastardly fall if we're not careful. Step one, know where you are. In chemistry, the problems that you're solving, you're typically going to, and it's not just chemistry, physics, algebra, trigonometry, you're given something, some information. It's just a given. And in fact, in geometry, I believe they call that a given, right? So step two is your destination. So, you know, where you are could be, the starting point could be something like 101.0 kilograms as a given piece of information. The destination, if you read my notes, I illustrated with a young lady or somebody with a skirt on, you know, if that's a skirt, a triangular outfit. It kind of looks like a logic symbol, actually. Anyway, this dude wishes to deliver the flower to Dudette there, and that's the destination. That's the desired result, is to get from here to here. And in chemistry, this could be simply so many decigrams, because the problem asks, how many decigrams is 101.0 kilograms? In your life, this could be 10 years from now or something to that effect. So step two is to identify what the answer should look like. If you cannot say what the units of the answer are, then you don't know the problem, and you're going to probably get it wrong. I say probably because some people are good guessers. That's not enough to be a good guess. Okay? So look at the problem, identify the information that is where the starting point is, identify what is being asked as the destination. That will get you. When you fill in that blank, you will have an A on this problem. That's what that is. When you fill in that blank, you'll have an A in your life. You'll have your career, whatever it is. Whatever it is that you decide you want to be in that blank, you'll have achieved your goal. Step three. This is very important now. This is very important for the chemistry class. We're doing what we're going to be doing in chemistry correctly. You're going to build a bridge. Now, in general terms, whether it's a logic problem in chemistry or a logic problem in AP Euro, or whether it's a logic problem in physics, or if it's a numerical problem, to be a word problem, you're still talking the same process. Where am I starting? Where do I end? What will an A answer look like? And then how do I get from where I am to that destination? How do I get to the destination of an A? You build a bridge. Now that bridge could be a logical construct. It could be a series of premises that can logically then conclude with the answer that you need. It could be a legal argument. If A, then B. If B, then C. Ergo D, or something like that, right? It could be a legal argument if you're in law. You know, this is going to vary. The construction of the bridge, the nature of the bridge is going to vary depending on the problem, the type of problem you're trying to solve. For this particular specific section of chemistry, the bridge is going to be a series, yes, you can write this in your notes, a series of multiplication steps involving ratios equal to the number 1. Notice I have written where I am, 101.0 kilograms. I've written a destination equals blank decigrams. The presumption is, and I believe this is problem number 1 in today's notes. I think I just lifted it over. The presumption is I'm going to convert kilograms to decigrams. When I fill in this blank, I'll have my A on this problem. I'm telling you that you're going to accomplish this conversion by multiplying a series of ratios times this that will end up converting it into that. We're going to use, because it's a series of multiplication steps, we're going to be using math rules and properties. We can't suspend the math rules. We're always under the realm of mathematical PEMDAS and all the other regulations of math and rules of math. Okay, so in order to change this number from kilograms into decigrams, I'm going to multiply it by a series of ratios. Now that's a multiplication sign, and that will be the divisor that separates top from bottom, numerator from denominator of the ratio. And the ratio is going to cancel kilograms and eventually introduce decigrams. We're going to use a mathematical property that accomplishes this by multiplying this unit by the inverse of this unit. So I'm going to put kilograms on the bottom. I've got an equal sign here. If 2 plus 2 equals 4, and it does, I can't just throw in a multiplication here and still have it equal to 4. If I multiply that by something, more than likely it will not equal 4 anymore. There's only one number in the universe that I can put multiplying times this that will still allow the left side of this equation to equal the right side of the equation. What number? 1. I'm allowed to put times 1 here. Can even make it. It doesn't matter what's top and bottom. As long as that ratio, if the top equals the bottom, then that ratio equals 1. And I'm allowed to multiply this by that, and I haven't changed anything. This size of this thing will still be said to be equal to the size on the right. This meter stick will still be equal to this meter stick. It's the same meter stick. As long as I multiply the left side by a ratio that equals 1. I accomplish that by making sure the numerator, whatever is in the numerator, equals what's on the bottom, the denominator. It doesn't have to be 4 over 4. It could be hola over hello, because hola equals hello. It could be a different little language as long as it means the same thing. As long as hola equals hello, then I can get a ratio by doing a little manipulation. I can create a ratio that's equal to 1. Let me demonstrate. Let me get rid of the life high school comment. You can go forth and prosper. Maybe think about those things. You got my email address. You can always check in with me and say, Basel, I'm really interested in that. Let's write a book together. All right, let's do it. Approaching Life as though it were a chemistry problem by Basel and Smith, or whatever. Delgado. All right. We go to Home Depot. Here's what you do. Home Depot is that prefix table, remember? You go to Home Depot and you tell the guy, hey, guy, I got, wrong one. I got kilograms. Ayúdame. Give me some kilograms. 1 kilogram is equal to 10 to the 3rd grams. That's what the table says. By putting a G on both sides, I get the unit that's in my problem. I got this from Home Depot. The reason why I call it Home Depot, remember, we're building a bridge. You build bridge with materials. So we're going to go to Home Depot and buy the materials that we need. I need a statement about kilograms. Here's why. This is called a definition. 1 kilogram equals 10 to the 3rd grams. That is a definition. What do we know about definitions in terms of numbers that we've talked about? Anybody online know the answer to that? Of course not.
They're infinitely precise or exact.
Well, infinitely not precise, although you could argue that, but it has a different meaning than what I'm looking for. Infinitely what? Exact. Exact is the vocabulary word. Precise, used in that context, actually refers to the number of decimal places. They have infinite precision, but that doesn't mean they're infinitely exact. They're related. They are infinitely exact, which means when we go to multiply and we round off to the least amount of sig figs, anything based on this definition will have infinite sig figs, and the limit will come from the measured number, which is 101.0 kilograms. All right, now watch this trick. Notice I need a ratio equal to 1 with kilograms on the bottom. So I have a statement from Home Depot, 1 kilogram equals 10 to the 3rd gram. Now watch what I'm going to do. I'm going to divide both sides by whichever side of this equality has the term kilogram in it. Well, this side does. 1 kilogram, 1 kilogram. Now I'm not breaking any rules. I'm following the math rules. Kilogram cancels out, and I get a ratio equal to 1. 10 to the third grams over 1 kilogram mathematically equals 1. So I can now multiply this by this ratio without changing it. So notice that I put kilograms there first to cancel out with this. I'm analyzing the dimensions, dimensional analysis, and placing them where they need to go so that I cancel out and transform what I was given into what I was requested. I'm not done yet, but I'm getting closer. I'll explain that in a minute. So 1 goes in front of kilogram, and 10 to the third goes on the opposite side of this ratio. 10 to the third grams over 1 kilogram, that equals 1. I multiply this times that, it gets rid of my kilograms and gives me grams. Now think about it. Kilograms are bigger than grams. Grams are bigger than decigrams. Kilograms are much bigger than decigrams. So I'm actually getting closer to the answer. I'm going in the right direction here because I've gone from a very big unit to a base unit. And my next step could very well be to the next subunit or prefix unit. So it doesn't get me all the way across the chasm yet. By building my bridge with one step, one ratio, I've only gotten halfway, at least halfway across the bridge. Maybe it's only a third of the way, I don't know. What I do next, because I'm at grams, this gives me the units grams, I ask the Home Depot guy, hey, dude, can you tell me anything about decigrams? Can you sell me a construction material that relates decigrams to grams? He goes, yeah, I can. Because 1 decigram, if you look at the prefix table, 1 decigram equals 10 to the minus 1 grams. You're like, fantastic. Look what I need to do. I need to get rid of grams, and I want to get decigrams. In order to get rid of grams in the numerator position here, I'm going to multiply this by another ratio. Let me squeeze this over a little bit. Okay, we can still imagine that that's a little blank. I'm going to multiply this string here by another ratio that gets rid of grams. So I put that on the denominator position, and I look at that decigram statement. I went to decigram because it's in the answer, and it's the most logical next thing to ask. First, I asked about kilograms. Next, I asked about decigrams. I need a conversion factor equal to 1 that has grams on the bottom. Well, there's a gram. So if I divide both sides by 10 to the minus 1 grams, 10 to the minus 1 crosses out, grams crosses out, I get a ratio equal to 1. If I write 1 decigram over 10 to the minus gram here, grams will cancel. Madre de Dios. Decigrams is on top where I want it. I just have to do the math now. The math tells me that if I multiply 101.0 times 10 to the 3 times 1 over 10 to the minus 1, the units will be decigrams. Look, kilograms crossed out kilograms, grams crossed out grams, decigrams remain. That's my unit. So there's my math. So I can rewrite that, or you can get a calculator. 101.0 times 10 to the third, since it's the same base, 10 to the minus 1, since it's the same base, 10 to the third over 10 to the minus 1, you subtract exponents. 3 minus 1. I get 101.0 times 10 to the fourth. I'm not done yet, because this looks like scientific notation, but it's not. It's not true scientific notation, because in true scientific notation, I can only have 1 digit to the left of the decimal place. So by moving that decimal 2 powers of 10 to the left, I make this number smaller by 2 powers of 10. I add those two there, and I get, for my answer, I get 1.010, 4 sig figs, times 10 to the 6 decigrams. That's my answer. That's called unit conversion. I know that's a mess. I'm going to, in just 10 seconds, 15 seconds, I'm going to clear the screen. I'm going to work the problem crisp and clean. Same problem, and you can look at it, take a picture of it, whatever makes you happy. Step 1, write what you know. Step 2, write your destinations. What do you need to know? Step 3, build a bridge. You start off, you don't know. You don't know how many multiplication steps you're going to need. Sometimes you cross a bridge, and it's one span. They call them spans. The length of the bridge that's between the two supporting columns. Sometimes you cross a bridge, and it's a single span bridge. If you've ever gone down to the Keys, you cross the 7-mile bridge on the way to Key West, it's span after span after span. It's like clickety-clack, clickety-clack, clickety-clack. And every 10 feet, there's a set of poles holding up the bridge deck. It's multiple spans. Sometimes you have problems that have multiple spans. Okay? Step 3, build the bridge. So the first span of the bridge, we take that unit that we want to get rid of. Look at your units, because sometimes, look, if I'm telling you the swimming pool is filling up at 50 gallons an hour, and I ask you how many liters per hour this is, well, then you realize, wait, we're only changing the numerator because it stays hour on the bottom, the denominator. So you need to look at your units and you need to use common sense. You need to have your eyes open, your brain on, and say, what units am I changing? There's only one unit. This is not a ratio of units. It's not speed, distance per time. It's not weight, dollars per hour. It's not density, mass per volume. It's simply mass, a single unit. And so it's in the numerator position. It's over 1, kilograms over 1, if you want to think of it that way. So therefore, in order to get rid of it, I must put in my bridge span, I must put kilograms on the bottom. It's not in the answer. It's got to go. I have to transform it. The only way to legally transform it is by multiplying by the inverse of it. So that's what I'll do. Now I need a ratio that's equal to 1 that involves kilograms. I get that by going to Home Depot. You don't always have to go to Home Depot. If I ask you how many seconds are in 2.2 days, you don't need to look up days and minutes and hours on a table. You already know what that is. You're like, let's see, 60 seconds are in 1 minute, 60 minutes are in 1 hour, 24 hours are in 1 day. You didn't have to go to Home Depot to get that information, to get those equalities. Those are equalities. 60 seconds equals 1 minute. That's a perfect, exact set of numbers because that's a definition. And you can turn that into a conversion factor, a ratio equal to 1. Okay, that's a vocab term, by the way. Conversion factor is a ratio equal to 1 that's made up of the equality relating 1 unit to another unit. A conversion factor is a ratio equal to 1 that's made up. It's made up by comparing 1 unit to another unit. I think I changed the verbiage a little bit, but that's the idea. A conversion factor is a ratio equal to 1 made up from the equality relating 1 unit to another unit. That's the way I said it originally. All right, we need to get a conversion factor or a ratio equal to 1 that includes kilograms. So we go to Home Depot. Sometimes you go to Home Depot, sometimes you go to your shed and you pull a piece of wood out of the shed that you need. 60 seconds equals 1 minute is an example of something that you already own. 1 kilogram is 10 to the 3rd grams. Now, I can, each time I do this, I can go through the tedious process of dividing both sides by the unit that needs to be on the bottom of that ratio. I can do that and convince myself that I'm developing a ratio equal to 1. Or after a couple times of doing that, you just do this. You need a K plus here. Once you have realized what you're going to do next, you don't need to actually do it. Just do it up here. Instead of creating it here, you say, okay, 1 kilogram, 1 kilogram. 10 to the 3rd grams goes on the other side, 10 to the 3rd grams. You can actually accomplish the construction of the ratio equal to 1 right in place. You don't have to build it here and then move it to there. That's an extra step. That gets rid of kilograms. I'll illustrate that now. I'm now at grams. I check my units that I need to get my A, and I recognize grams will not get me an A. I have to have it in decigrams. So the next thing I'm going to do is I'm going to ask Home Depot, what is a decigram? And I see that 1 decigram is 10 to the minus 1 grams. Now watch what I'm going to do. I'm not going to build the ratio here as I did over here. I'm going to build it in place. So I put in another multiplication. I don't like to just assume it's going to be 2 steps. Sometimes it's 1, sometimes it's 3. There's a situation where you may have 4 or 5 steps. I got to get rid of grams, so I'm going to put grams on the bottom here, the inverse. Now, here's my statement that relates grams to decigrams. 10 to the minus 1 gram goes on the bottom. 1 decigram goes on the opposite side. Grams cross out. I can now simplify 101.0 times 10 to the 3 over 10 to the minus 1 equals 101.0 times 10 to the 4. Move this, whoever was asking, here it is. 1, 2 places to the left. I add the 2 there. This becomes 1.010 times 10 to the 6. 1.010 times 10 to the 6. Any questions? Convert 4.92 times 10 to the 8 micrometers to kilometers. Step 1, write what you know. 4.92, that's the given. That's what we know. We don't know the other thing. Step 2, write what we need to know to get our A. So we put an equal sign. All right, step 2 was to write your destination. What's going to get you to A? Step 3 is to build a bridge. So I don't know how many steps it will take to build that bridge. I'll start with 1. I got to have at least 1 span, otherwise I'm not going to get across there. So I have to go to Home Depot and I have to ask them about micrometers. What is 1 micrometer, Mr. Home Depot person? Well, I learned that 1 micrometer is 10 to the minus 6 meters. Now your table only says 1 micro is 10 to the minus 6. You supply the unit meters. Whatever unit you put here, you put here. I can go up here because I want to get rid of micrometers. I put it on the bottom. That's the inverse position. I look at this equality. 1 micrometer, I put a 1 in front of micro. Again, notice I do not start with the numbers. I start with the letters. That's what makes it dimensional, and that's what makes it analysis. I'm analyzing the process required to get rid of that unit. That's why it's dimensional analysis. It's not dimensional randomness. I'd really like you to dimensionally analyze the problem and solve it that way. Put the micrometers on the bottom. 1 micrometer, 1 micrometer. 10 to the minus 6 meters is on the opposite side. So 10 to the minus 6 meters. Now, we check that unit because that unit's now gone. Check that unit. It's not the correct final unit. So let's go ahead and go to Home Depot again and say, hey, Home Depot, What do we know about kilometers? It's equal to 10 to the third meters. So let's try another conversion step. We might need a third. Sometimes you do. We put meters on the inverse position. Meters has 10 to the third in front of it. You see, it's the unit that guides you where to put the number. Don't just randomly multiply or divide. And then on the other side is going to go 1 kilometer. And as I said earlier, Madre de Dios, kilometers is in the numerator position in the answer as well. That is my conversion process. I now group together my powers of 10. This is what I love about scientific notation. 4.92 times 10 to the 8th times 10 to the minus 6 over 10 to the third. And all of that gets grouped together as 4.92 times 10 to the 8 minus 6 minus 3. 4.92 times 10 to the minus 1. 8 minus 6 minus 3, that's minus 9. So you can either write 4.92 times 10 to the minus 1 kilometers, or you could write 0.492 kilometers. Either one of those would be correct. Mr. Snail is traveling at 17.4 centimeters per minute. I want to know, many understand that there's an important step that was missing from my high school education that I'm going to try to give you, and that's this advice. You do not have to handle both the numerator and the denominator together. You can separate them and deal with one at a time. Step 1, we're going to write what we know, which is 17.4 centimeters per minute. Step 2 is to write what we need to get our A, which is blank millimeters per second. Step 3, all right, build a bridge. Step 3, build a bridge. Now, do yourself a favor and focus on one unit. Do not try to see centimeters per minute as a whole. It's a ratio of two different things. Let's focus on distance. Let's focus on the numerator. I'm going to get rid of that numerator by putting it on the inverse position here. I now go to Home Depot and I say, hey, Home Depot, what do you know about centimeters? I know that 1 centimeter is 10 to the minus 2 meters. That's from Home Depot. Or you should have that in your brain, because you know what cents are in a dollar. 1 cent is 0.01 of a dollar. Okay. So 1 goes in front of centi, 10 to the minus 2 meters goes on the other side. Does anybody not understand why I'm doing that? That gets rid of centimeter, and I now have meters. In my answer, the numerator is not meters, it's millimeters. So again, ignore the denominator, and let's just focus on distance. What do I know about millimeters? 1 millimeter is 10 to the minus 3 meters. So I'm going to continue multiplying or building my bridge. I got to get rid of meters, so I put it on the bottom. 10 to the minus 3 goes in front of that. I hope everyone sees that I choose the unit in the inverse position, and then I tack on its appropriate number. Do not do it the other way. Do not put the number, otherwise you'll be guessing top or bottom. Okay, 10 to the minus 3 meters is on the bottom. 1 millimeter is on the opposite side. And as we say in my país, Madre de Dios, mira, it's in the top position. It's correct. All right. We have now converted distance from the unit of distance given to the unit of distance required. We're still stuck with minutes. We've not done anything about the denominator. Let's do something about the denominator. One more step. And since minutes is in the denominator position here, what would the inverse position be? I'm multiplying by the inverse of 1 over minute. It goes in the numerator, top position here. And I don't need to go to Home Depot. I happen to have out in the garage a nice board that I could use, and it's called 60 seconds equals 1 minute. I already know this. 60 seconds equals 1 minute. 1 goes in front of minute, 60 goes in front of seconds. Minute cancels, and I have 17.4 times 10 to the minus 2 over 10 to the minus 3 times 60, like that. You punch that in your calculator. Don't try to do that. I mean, you can get rid of the powers of 10. You end up with 17.4 times 10 to the first over 60. That's called scientific notation. 17.4 ED1, or you can just do 174 divided by 60. I need 3 sig figs, so the answer is 2.90. 2.90 millimeters per second. I'll be posting this. I think we're done.